Next we have YouTube. Okay, we have audio also. Okay, your turn.
Did we do 7 on 14? I think we both made that.
On homework 14.
Yeah,
When is that homework due?
I think Friday. Yeah. Friday.
Is it?
Wow.
Okay. Which one? 7?
Yeah.
So the temperature near the surface, you have kinetic energy. Okay, problem 7 on homework 14. So they give you the temperature. They give you the mass of an argon atom. With average kinetic energy. And no collisions with other atoms and molecules. How high up it would go before coming to rest? Assuming, so this is an assumption that is a little bit too strong. The acceleration due to gravity actually is going to drop, but for our purposes, we're going to assume that the acceleration due to gravity doesn't change. And look, you have that the average kinetic energy, 1/2 mv squared, has to be exactly equal to 3/2 kT. Right, this is the average kinetic energy. So they give you everything well, they give you the temperature. You have to convert the mass that they give you from atomic mass units into kilograms. So there is a conversion factor somewhere in the textbook, or you can just use Google to do the conversion factor. And from there, you find that the average speed of that molecules is going to be equal to what? 3 kT divided by the mass under square root. This is the average speed. And that's it. And after that, do kinematics. Say initial velocity equal to the velocity that is this expression. Final velocity, so this is initial. Final velocity is 0 when you're up, right? You're launched with this average speed. And the acceleration, they say, is constant and due to gravity. So in this coordinate system, the acceleration should be a negative number if you use a coordinate system like this. Or x-axis. Yes. So you have your 3 numbers. Find the displacement in vertical direction, let's say y. This displacement y, right? You're going up and you have to let going down. And you need a formula that doesn't include time. And the formula that doesn't include time, the kinematic formula that doesn't include time is v squared is equal to v naught squared plus 2 times acceleration multiplied by the displacement that you're looking for. Well, final velocity is 0, so you're going to get negative v naught squared is equal to negative 2g. Right. Therefore, you have that the highest point that you're going to reach is at height y equal to v naught squared divided by 2 times g. So v naught here is actually, v naught here is what you calculated, the square root of 3 kT divided by the mass.
Did you get the negative 2gy because The acceleration is negative.
Yes,
Oh.
yes. In this coordinate system that I have chosen, the acceleration is negative 9.8, negative g. This is. So I gave this problem because, well, keep in mind that when you take into account that as you go up, the acceleration due to gravity drops. From 9.8, it becomes 8, 7, and so on. So this means that in reality, an atom is going to reach far enough. And actually, if the mass of the atom is small, its average velocity is going to be larger, and it is going to be sufficient to get out of the gravitational field of the planet. And this is why, of course, geologists know why we don't have, for example, free helium around. Just because it is an atom with small mass, and at average temperature that we have on the surface, every helium atom eventually is going to fly away, or at least most of the helium atoms have broken loose from the gravitational field. Okay.
Is the atomic mass unit, the U at the end, is that Dalton? Is the unit itself, is that what that's called? When I would
Yeah, well, I don't know the notations in the textbook. Yeah, I think that this is the notation in the textbook, U for atomic mass unit. So defined as 1/12 of the mass of the carbon-12. So it is practically very close to the mass of the proton. So if you have it at the table with the mass of the proton, just take that mass in kilograms, and it's going to times 39.4948, and it is going to give you the correct answer. But atomic mass units is defined somewhere in the textbook. It should be somewhere. Yeah. Okay. Other questions?
Can we do number 11 on homework 15?
On 15. Oh, 11. Yeah, we didn't talk yet about refrigerators, but well, it is. So problem number 11 from homework 15. So it is a refrigerator, ideal refrigerator, the best refrigerator you can design. And they say that the inside of the refrigerator has this temperature. The temperature of the kitchen is some other temperature that is given. And you're buying a certain number of joules of energy from the power company. In the case that is on the board, it is 2,600 joules of energy coming from the power company. How much heat can this generator, can this refrigerator remove from the inside of the? So look, all problems related with refrigerators, heat engines, heat pumps, you always start with a diagram representing your device, and the diagram looks similar for different devices, but it is different in the direction of energy flow. So the hot reservoir of the refrigerator is at temperature TH, the cold reservoir is at temperature TC. And so the cold reservoir of the refrigerator is the inside of the refrigerator. The hot reservoir is the kitchen where you're going to dump heat. So you want the refrigerator to remove heat from the cold place, and that heat is QC, and dump the heat in the hot place in the kitchen where the temperature, the heat amount that is going to be put there is QH. But this means that you want heat to move from cold to warm place, which is not natural direction of motion. So you have to force it, you have to force the heat flow in that direction, and you achieve that by doing some work from the power company. Now, energy in this ideal case is conserved. So those two energy flows form the total energy that is going to be dumped in the kitchen. In other words, QC plus the work is equal to QH. So in this problem, they tell you that the temperature of the kitchen, the temperature of the hot reservoir is 319 Kelvin. The temperature of the inside of the refrigerator is 277 Kelvin. They're asking you how much heat you're going to remove from the cold place. They're asking about this, but they just give you the amount of work that they don't give you QH. So you need some additional information. And that additional information is based on a quality that is not derived in the equation, that is not derived in the textbook, but it is kind of close to common sense. So for any engine, refrigerator, ideal engine, ideal refrigerator, air conditioning system, the ratio of heats is equal to the ratio of temperatures. So you can prove this by using the concept of entropy. And again, I'm calling this, the proof is trivial, but again, we don't know yet what is entropy, and it is not given in the textbook. So just take this expression as a magic formula. It solves all problems related with engines, refrigerators, and so on. So in our case, temperatures are given. You're looking for this. QH is not given, but you can say that from the conservation of energy that I wrote, you can say that, well, I can just substitute QH with its equal right here. And I'm going to get QC divided by QC plus work. Is equal to the ratio of temperature, Tc divided by Th. And now it looks like everything is given except QC, so you can solve for it. You can solve in different ways. How to do it, Well, the algebra can be done in multiple ways. How to do it fastest. Okay, let's do it this way. Take this expression and take its inverse. In other words, raise both sides to power -1, which is going to make numerator denominator and vice versa. So you have, this is going to be the same thing as QC plus work divided by QC is equal to TH divided by TC. This last equation looks like this. If you modify the left-hand side, it is 1 plus work divided by QC is equal to TH divided by TC. And now you have to solve for QC. So you're going to say, I'll continue right here. So you're going to have work divided by what you're looking for, QC, is equal to TH divided by TC minus 1. And after that, you can again change the order, or you can just write that QC is equal to work divided by TH over TC minus 1. And this should be the answer. So this is QC. So it is algebra. Is there faster way to do it? Well, probably there is a faster way to do this problem, but this is, yeah, I could have substituted. I could have expressed QH here and substituted here, but it probably is going to be pretty much the same. Okay. Any remarks here? Okay. Other?
I'm not sure if you did this before I got here, but have you done 12 yet
Problem 12 from which assignment?
from this one?
No.
Okay.
So it is a similar story, but again, I haven't talked about heat pumps and refrigerators. Yeah. So let's do this problem. But again, all problems of this type, you start with the diagram, and the tricky part of the diagram is to know from reading the problem to figure out direction of energy flow. So problem 12 from the homework assignment on chapter 15 is about a heat pump. And we assume, of course, that this heat pump is used in the winter for heating the inside of the house. So always on top you have the hot reservoir with temperature TH, on the bottom the cold reservoir with temperature TC. Now the hot reservoir for you is the inside of the house. The cold reservoir is the outside environment. And you want more heat to go into the hot place. And ideally, you would take this thermal energy from the cold place. But this means that you want to force heat to move from low temperature to high temperature, which can be only done by doing some work. The power company is going to. But still, you have certain free amount of energy, thermal energy that comes from the outside. You have to pay a little bit to force it to go in direction that you want to go, but heat pumps utilize free heat from the outside, certain amount. The first question is, well, they give you, in my version, they give you how much heat is taken from outside. For my version, it is 2060. So QC for me is 2060 joules. And they say that the total amount of heat that enters the house is, for my version, QH is 3,140 joules. So the first question, how much work does the heat pump need? Well, if you look at conservation of energy, merging QC with work gives you QH. Therefore, the work that you have to purchase from the power company is equal to QH minus QC. So the difference of the two heat flows that. So this is part A. Just conservation of energy gives you part A. Part B, they're asking you to figure out the coefficient of performance of this heat pump. So notice that in this situation, you're taking 2,060 joules of free heat from outside, and you are spending only about 1,080 joules you're purchasing from the power company. 2,060 is free, 1,000 something is what you pay for. By definition of coefficient of performance is always defined, so K, coefficient of performance, is always defined as what you want divided by the price that you pay for it. Well, what do you want from this heat pump? You want more QH. What is the price that you pay? The price that you pay is the work. And that's it. So you have QH, right? It is, for me, it is 3,140. The price that you pay is, we just found it to be the difference of QH and QC, right? Just divide those two numbers, and this is your coefficient of performance. Yeah, I wonder. Okay. Okay, so what other problems? So this problem is not that difficult. It is just to remind you the definitions for. Yeah.
I do have a question about the diagrams. How do you decide which direction the QC and the QH are going to flow?
By thinking of what device we have and what is what in this device. So for a heat pump, it is a heating device. And the inside of the house is the warm place. And you want to add additional heat to the place that is already warm. So it is just by reading the problem and thinking what is happening. So a heat pump is a device that has to take heat from the cold outside and bring that heat in the warm house inside. So just from the nature of the device, and I don't remember actually, I'm just reading the problem, and from there I decide what is hot reservoir, what is cold reservoir, and in which direction you want to move the energy.
So it's like, because yesterday we had the example of the car and it went the other way.
Yes,
Trying to cool off.
yes. So in the case of the car, it is a different story. You drain energy from the energy stored in the fuel, and part of that energy you generate work, you get work out of it. But the second law of thermodynamics can be shown to require part of the energy that you drew from the fuel to be lost, to be dumped in the environment. It can be shown that this is a must. There is no other way. So this is why, we're going to talk again about that, maybe tomorrow in class, shortly, because we have to do this standardized test. I hope that the attendance tomorrow is going to be better, because this test is going to go to the administration eventually. And we're going to suffer if we don't have the attendance. Well, I'm going to suffer. You're not. Nobody is going to say anything about it. Okay. Other questions? Problem 15. Let's see. So, did I solve this problem? Sounds familiar. Oh yeah, I solved it after class. Somebody asked about this problem. So you have a refrigerator, and look, for this refrigerator, I'm going to draw the same diagram. So, okay, problem number 15 from the homework assignment from chapter 15. So you have a space heater that they give you the power of the space heater. And look, power is defined as work or energy. Let's do energy divided by the time interval. Energy change or work. So they give you the power. The energy that this space heater is going to deposit in the house is given in terms of the workings of this refrigerator. So we have to figure out this amount of energy. And after that, you can say the time this space heater has to work should be the energy divided by power. So the power is given, the question is to figure out this energy. And actually, instead of the letter E, I'm going to use Q because it is thermal energy eventually, right? It is thermal energy. Well, now let's think about the refrigerator. Here is the hot reservoir always on top. And after that, the cold reservoir with temperature Tc. And now, where is the cold place of the refrigerator? Inside the refrigerator. So you want to remove heat from inside the refrigerator, from the place that is already cold. And you want to dump that heat at the only place that is available in the kitchen. So QH, the hot reservoir, is the kitchen. There is no other way. And again, you want heat to move from cold to warm place, which can only happen if you force it by doing work. So let's see what we have here. We have a refrigerator with given coefficient of performance, and it freezes certain amount of water from 22 into ice at 0. So they tell you that the amount of heat this refrigerator extracts from the water is going to be equal to the amount of heat that you have to extract from water, from 1.25 kilograms of water, so mass of water, to bring this water from temperature 22 to temperature 0. So this is 22-degree difference. So heat capacity of water. This is the amount of heat that you have to extract from the water to make it water at 0. But after that, you have to freeze this water and create ice at 0. So you have to extract additional amount of heat equal to the mass of this cold water now, multiplied by the latent heat of fusion for ice water. So here, all the numbers are known. Heat capacity of water is known. Latent heat of fusion is known. This is the amount of heat QC. Okay, okay. But look, in reality, the heat in this equation has to be the heat that is deposited in the kitchen, which is QH. So you have to find QH. And look, coefficient of performance is defined as what you want divided by what you pay for. So from the refrigerator, you want QC, and you pay for the work. They give you the coefficient of performance. You just calculated this. You can say that the work that you have to buy from power company is equal to QC divided by the coefficient of performance. And you have that number now. And after that, you just say those two energy flows combine and give you QH. So you know QC, you know work. Add them up, you have the heat that is deposited in the kitchen, and after that, you calculate the time. They want the time in seconds. If you use SI units, you're going to get the time in seconds. So kilowatts is 10 to the third watts. So power is 4,500 watts. Okay. Other questions?
So then for 16, it would be pretty much the same process. You would just flip around the variables because you're trying to find.
Yes.
The math
So the
this
numbers are, oh, it is practically exactly the same.
Yeah.
Why did I?
Okay.
Yeah, practically the same. Yes, practically the same. But well, you don't need here to find QH at all. But you need to you have to use exactly the same philosophy. Exactly the same philosophy. you have to calculate here the work. Yeah, it is exactly the same philosophy, but you have to be careful a little bit. So ignoring work that find the maximum amount. So here you have to solve for the mass of water or ice. Try it independently, and that will help you make sense of the entire story. Again, we didn't have time to talk on Thursday about refrigerators and heat pumps and so on, but we have to do it. Maybe after the break, we're going to talk about those devices again. Okay, let's see other questions. Other questions?
Let's do 14.
Let's see. Yeah, we didn't even define entropy so far. Entropy is the last section in chapter 15. Okay, now I remember why I changed the due date for chapter 15 homework, because we didn't talk about entropy. But, well, entropy is a tricky subject. We just have to talk about it. So, and actually this entropy is an important subject also for biological sciences. And we, in this classical way of studying thermodynamics, we don't have a very nice definition for entropy. So entropy is the measure of how chaotic a system is. So very chaotic systems have high entropy. Well organized, well ordered systems have low entropy. But the connection between entropy and the thermodynamic variables that we're familiar with looks like this. So this is problem 14, right? So for us, defining variable of entropy comes via the formula which says that change of entropy S is equal to the amount of heat added or subtracted divided by the temperature. Here, this formula only works when you are adding and subtracting heat, but the temperature doesn't change or doesn't change substantially. So delta S is the change of entropy. The amount of heat in this formula is going to be a positive number if you add heat, if the object gains heat, and it's going to be a negative number if the object loses heat. So for problem 14, you have a star with certain radius and certain temperature, surface temperature. Determine the amount by which the star thermal radiation increases the entropy of the universe every second. Assume that the star is perfect black body and the average temperature of the rest of the universe is 2.73 degrees Kelvin. do not consider the thermal radiation absorbed by the star from the rest of the universe. So look, here is the star. It emits heat, doesn't absorb any heat from outside. Its emissivity, they say, is 1, perfect black body. They say that the temperature of the star is constant. The temperature is 6,150. So look, you have the temperature, you have the amount of heat, the amount of heat that the star loses is going to be Stefan Boltzmann constant, emissivity, surface area. Well, the surface area of a sphere is 4 pi the radius squared. And they give you the radius, so you know the surface area of the star. And this has to be multiplied by the temperature of the star to power 4, and they say per 1 second, so T is 1 second here. So in this equation, you know everything, and you can calculate the amount of heat that is emitted by the star. So you're going to have the change of entropy delta S of the star is going to be negative this heat that you calculated with negative algebraic sign divided by the temperature of the star. And you see that the star is going to be losing, the entropy of the star is going to be dropping, because you have negative Q. So the star gets more organized, better, as it loses energy and its entropy drops. On the other hand, the rest of the universe absorbs this energy, this heat. And of course, it stays at temperature 2.73 because this universe is large. And therefore, you have the change of entropy of the rest of the universe, delta S, is going to be equal to the amount of heat with positive algebraic sign now, because the rest of the universe is receiving it, divided by the temperature of the universe, which they say is 2.73 degrees. This is the increase of the entropy of the rest of the universe. So determine the amount increases the entropy of the entire universe per second. Well, maybe the net increase, the universe includes the star also, right? So the change of entropy, net change of entropy of the entire universe is going to be this plus this. This is a negative number, this is a positive number. So it is going to be delta S plus delta S prime. In other words, it is going to be negative Q divided by T, positive Q divided by 2.73. And look, you're going to see that this temperature, since the temperature of the star is 6,000, this divided by 6,000 is going to be quite small number. So practically, the second term is going to be the leading term. This is only a small correction if you think that the universe, if they're asking about the universe, that includes the star also, right? This is strictly speaking. This is the way of reasoning.
So the Q is the same for both of them?
It is the same because whatever energy, whatever heat the star radiated, this is the energy that the rest of the world took in. Right? That's the philosophy.
It's only negative for the star because it's putting it
It is
out.
losing it.
It's
Yeah,
putting it out.
the star is losing it, so this is why it is negative. But that negative number is small compared with the other number, which is much larger. Because the negative number you divide by 6,000 and something. Here you divide only by 2. So this term is a small correction. Strictly speaking, yeah. And in a similar manner, actually, you do problem number 13. It's not much different. Okay, let's see other questions. So somebody sent me a problem, a classical mechanics problem. Probably from some standardized test. Let me see, where is it? This problem right here. So I don't know how much of this problem is visible. I can reduce the size. Something like this. So look what they say. A large wheel with radius and moment of inertia is able to rotate. And now you have a bullet with given mass and given speed is going and hitting the rim of this wooden wheel, and it is lodged in the wooden wheel. If the wheel was originally at rest, what would its angular speed be after the collision? So this is a problem, actually, not bad problem about conservation of angular momentum. So the angular momentum L before should be equal to the angular momentum after the collision. At the instant when the bullet is just about to hit, but it is not there, the angular momentum is of the system is only due to the moving bullet, and that initial angular momentum is equal to the mass of the bullet multiplied by its speed. Let's see what letter they ask. Well, multiplied by the speed of the bullet, multiplied by the radius R, capital R, of the wheel. So we haven't had in this textbook a question of this type, but it is a typical question because look, you can say, oh, but there is no rotation before the collision. How come that before the collision I have some angular momentum? So we haven't encountered, I may have had some conceptual question of this type, but this is the angular momentum of an object that is moving with respect, of course, to this axis of rotation. Well, after the collision, the angular momentum after the collision has to be equal to the moment of inertia of the system multiplied by its angular velocity. By the way, you can interpret this by saying, well, this is something like angular velocity of the bullet just before the collision. Yeah, well, doesn't look like angular velocity, but well, this is what we have. This is what it is. So after the collision, you have some moment of inertia and some unknown angular velocity. So let's see. They say that, well, in our case, the moment of inertia of the composite object that consists of a bullet embedded here at the rim, and the wheel is going to be moment of inertia of the wheel, which they say is given, plus the moment of inertia of the bullet with respect to that axis of rotation is equal to the mass of the bullet multiplied by the radius of rotation squared. And that's it. In other words, here you have moment of inertia of the wheel plus mass of the bullet times the radius. And all of this has to be multiplied by the angular velocity. And now you say this should be equal to this, and that solves the problem. So you're going to have moment of inertia of the wheel plus the mass of the bullet, the radius of the wheel squared, multiplied by the unknown angular velocity has to be equal to the mass of the bullet times the speed of the bullet times the radius. And from here, everything presumably is known, and you can solve for the angular velocity, and you get the angular velocity is mass of the bullet, velocity of the bullet, the radius, divided by the moment of inertia of the wheel plus the mass of the bullet, the radius squared. So that's I don't know, this problem should be from some online course or something, but this is how you do it. So how to justify this expression with the formulas that we have encountered so far? Yeah, you can justify it by saying, here is the wheel, here is the bullet just before it hits. Here is the radius. So you can think that this bullet is moving with the speed of the bullet, and you can think that at that instant, its angular velocity is equal to the speed of the bullet divided by the radius of rotation. But the moment of inertia of the bullet is the mass of the bullet times the radius squared. And the angular momentum is going to be product of moment of inertia of the bullet times angular velocity. So it is going to be v bullet divided by the radius multiplied by the mass of the bullet, the radius squared. Squared cancels with this, and you get what we had. But you probably don't want to think in those complicated terms. well, again, one issue with the textbook that we have is that we don't use vector notations for angular momentum, angular velocity, and so on. And this comes and hits us. We have to do some mental tricks in order to justify some equations. But this works, I think. So whoever sent me this problem, it's a good problem, but you see that the solution is not trivial, because the initial angular velocity, I had to, well, it is not exactly hand-waving argument, but it is something that is not exactly transparent. Maybe I should have considered a situation similar to this one when we talked about angular momentum of a system. But for the moment, this should be it. Okay, let's see questions about this problem or other problems. Problems? Well, it's more than 1 hour, so let's end it here then. And please be here tomorrow if you can for this standardized test. Okay, have to stop.